the star-forming region in the northeast quadrant section of the galaxy. Zoom in and take a look. We see these are high mass, high luminosity stars. These are O and B class stars. Okay, triggered by rapid star formation or prodigious star formation brought on by this rapidly rotating black hole, 2 million solar mass black hole in the galaxy center. All right here. You see background way in the distance, another galaxy right here. The gas and dust left over from the stars from these stars formation is what we see here. These stars, some of them are still embedded inside that gas and dust, and that's hot. And remember, this is an infrared image. So in the infrared, it's heat we're looking at, not light. Okay, so what you're seeing is, well, clearly you see the stars here, but the red areas are the gas and dust that are left over from the stars formation, and they're being irradiated by the stars. The intense radiation from the star inside is causing it to glow in the infrared because it's very hot. And if we zoom out a little bit, this is the image we just created. You can see these myriad field stars here. These field stars are A and F class stars. At the limit of detection for the James Webb Telescope at 55 million light years would be magnitude 33 or 33.5. That would be an early F class star, an F0 star, or an A7 to A9 star would be in that range. So the A0 star would be a little bit brighter. So these stars that looks like sand, grains of sand on a beach. Okay. In this bar, this is the Barred-Spiral Galaxy. You see this here? Here's the bar. This is called the Great Barred-Spiral Galaxy. Made up of mostly stars. There's trace amounts of gas and dust here, but most of this bar consists of these myriad A-class stars. Stars like the star Vega. If anybody's familiar with the movie Contact, the star that was made famous in that movie is Vega. Okay, Vega's an A-class star. It's like an A0 or an A1 class star. Okay. These bright stars are foreground stars in our own galaxy. Any stars that we see at distance would not be a star such as this. That's too bright. That's a field star in our own Milky Way galaxy. This central blue spot is the region where the black hole is. This indicates a nonlinear increase in intensity and heat. As this gas spirals in towards the black hole, frictional heating elevates its temperature to millions of degrees. Okay, and it causes it to be an X-ray source. Thermal sources in the million-degree range emit X-rays. Okay, so that blue disk represents the central region of the galaxy's core, and at the very center is where we have the 2 million solar mass rapidly rotating black hole. Okay, so that blue spot or that blue disk indicates a nonlinear, very drastic exponential increase in intensity and heat as the gas spirals in towards the black hole. It's being heated up by friction as the one layer or one stream to the next. The gradient, a very sharp gravitational gradient, causes it to heat up as it spirals in towards the black hole. So that's what that is. Okay. This is a very interesting nucleus. Here we see another star-forming region here. Right here. Well, these are hot, luminous O and B class stars, surrounded by the gas that's still left over from their formation. Star-forming regions are seen also in the galaxy's lower quadrant. This would be the western quadrant down here. These are all star-forming regions, pretty much the same situation as the eastern quadrant above. Okay, you can see these distant galaxies. These are galaxies way beyond in the distant background of this galaxy. Okay. This one is of particular interest, this edge-on spiral right here, way in the distance, right here. Okay. Zoom in on it. You can see other faint galaxies almost at the limit of detection here and here. As we look at the core, we can't help but notice the brilliance of the swirling gas, the luminous stars, and the stunning pink star-forming region. New, high-mass stars are embedded in this cloud and are heating it up. In the infrared, we can see through this leftover gas and dust and observe the embedded stars inside. The outer bands of hot, swirling gas are about 6,500 light-years from the core. The entire core measured lengthwise is about 13,300 light-years. Okay, if we consider the inflowing gas to be a thermal source or a source of heat, then at almost 7,000 light-years from the black hole, the spiraling gas has been heated to about 1,000 degrees Kelvin by differential frictional heating. Okay, if we consider this too, this is mostly in the 3.6 micron image. This is really red. Okay, the thermal source is about 1,000 degrees. Not much at this distance. Okay, that's not really a big deal. But as the gas spirals ever closer, the frictional heating continues to increase, with the gas temperatures reaching into the millions of degrees, spiraling closer and tighter, getting hotter and hotter as the stream of gas approaches the black hole. As the gas impinges on the black hole's event horizon, the gravitational gradient is now enormous, and that causes the inflowing gas to become relativistic, or it's approaching high velocities close to the speed of light. Okay, and in fact, there's a paper, I'll provide a link in the comments section. A recent paper measured that to be true, that the inflowing gas, this is one of the most dynamic active galaxies. As I mentioned earlier, this galaxy is what they call an active galaxy, where the central rotating black hole is active. It's drawing gas into itself, it's feeding on that gas, and it's causing rapid star formation in other regions of the galaxy. We call those galaxies active galaxies. So that inflowing gas is approaching relativistic velocities because of the intensity of the black hole. Okay. The images published here are integrated composites compiled from 3 grayscale images, as we see now, right? We just went through this exercise with PixInsight, each a different wavelength in the infrared. The digital processing software, PixInsight, measures the relative intensity of each grayscale image on input. Okay, the spot at the center of the core image is a direct indication of the intensity at this location. Since this color was assigned to the 2 micron waveband, this indication indicates a nonlinear increase in intensity at this wavelength, right? The width of this spot is 40 pixels. Okay, I measured this. Thus, the width of the region is 675 light years at the particular scale, which is 17 light years per pixel. The intensity, understood to be heat in this context, is increasing at a nonlinear rate for the 340 light year region surrounding the black hole. This result is consistent, okay, with what we just described earlier and just previously about the inflow becoming relativistic as it approaches the event horizon of the black hole. In the article, in the full-featured article on our website, I quote some of the abstract from a couple of the papers that were published describing this environment at the center of this galaxy. Okay, in the images, we can see, when we look at the core, the gas being drawn in. The turbulent inflow of gas and dust has triggered a flurry of star formation, clearly manifest in the star-forming region in this image. The lower left quadrant, the third quadrant of the image, you can see this. Active star formation is also observed in the image all the way at the top in the eastern section, that eastern arc, that star-forming arc. Okay, that arc is 50,000 light years from the galactic center. So that whole section, one half of that galaxy, that one half of the bar is 50,000 light years in extent. In our full-featured article also, we have download options. Okay, Okay, if anybody's interested, there's various images you can download. They're large. They're JPEGs, PNGs, TIFFs. Anybody's interested in downloading the post-processed FITS file, please, those are available upon request. Okay? Those are available if anybody's interested in these. Okay, we provided the 2, 3, and 3.6 micron grayscale images if anybody's interested in looking at those. And if you look at the article posted on our website, put a link in the description below. Towards the foot of the article, there's various download options. If anybody wants to download them, please feel free. But if you do use them or make mention of them in any publications, please do mention us. That's the only thing that we'd ask. Okay?
This is Dr. Jim Daly of Astronomy for Change. May you come to love the stars too fondly to be fearful of the night. And remember, the Earth is a mote of dust floating in a sunbeam. That's reality. Everything else is just marketing. The great philosopher Plato famously said, "Astronomy compels the soul to look upward and leads us from this world to another." Astronomy for Change is a non-profit organization whose mission is to effect a positive change through astronomy and science education. It is our belief that by inspiring and empowering current and future generations to become interested and engaged in astronomy and science, this positive change will be realized.
If you enjoyed this video or found it educational or useful, please consider subscribing to our YouTube channel and sharing the video. These actions on your part are free to do and will help us grow. Also, why not consider supporting us by leaving us a tip or buying us a coffee or perhaps visiting our Patreon page? Any amount would help and would be most appreciated. All the links and details are in the comments section below. And, as always, thanks for watching.